Good afternoon, everyone, and good afternoon, Daniel.
Hey, everyone. Nice to be here with you.
Okay, so let's start. So this is a stream, but if of course it's going to be recorded, it is recorded and it will be live right after on our YouTube channel. So topic today is Quantum Unreal. First time we actually show this publicly on a stream, or we've showed to a couple of people before. There are a couple of samples built, but this is really the first time we're going to talk about it. But before we start, just a few announcements. So I'm Eric, senior engineer at Photon. I think this here helps. Little mistake. And this is Daniel. Daniel, can you introduce yourself?
Yeah, sure. So, I'm the lead physics developer on Photon Products, Quantum Unity, Quantum Unreal. So yeah, everything physics wise.
And of course, also really involved in general quantum and quantum unreal topics. Um, yeah, today we're going to talk about mostly about quantum unreal. We're going to show the SDK, program a few things, show how it works, and all the differences it has from regular quantum, how it relates to normal ways you program with Unreal and everything. But of course, you're also welcome to ask any question about quantum in general or any photon product in general. Of course, we're not gonna answer, oh, how do I fix this on my game, but it depends on the question. We may comment on how the topic works and so on. So feel free to ask, and we'll let you know if it's possible to answer this or not. Um, I'll just do a quick check here that audio is good and everything is good. So if anybody wants to comment on the chat, um, we will appreciate that. Just to make sure audio is good for everyone, and then we can start. Thank you, Miroslav. So that's enough. Let's start then. So let me switch screen here. So we do it like this. So I have here actually our repo that we use to develop the SDK itself, but I would like to start showing how this all works if you are used to Unreal. If you're not used to Unreal, we'll try to add a few comments as well. So this here is a regular, let's say, the structure of a regular Unreal 5 project, very similar to Unreal 4. And normally you have all your C++ source code inside the source folder, and it will be no different here. Quantum itself is distributed as a Unreal Engine plugin. So you can have your Unreal project, and then you can import the Photon Quantum plugin into it. It comes with a bunch of stuff in source code. It also comes with some libraries that are physics engine, the quantum Predict-rollback stuff, uh, pre-built for all the platforms you need, binary libraries. But a bunch of all the whole Unreal integration and everything is distributed in source code. There will be a bunch of add-ons that will be distributing over time as well. Like it's actually as part of the SDK of the project here, and I'll show a couple of things here. For example, so we have some interesting vehicle physics built in and a basic character controller built in, but these are going to be improved a lot and distributed as, let's say, separate add-ons packages that reference the original plugin. But for now, they are in our demo project here that anybody who has access to that will have access to the SDK will have the source code. The idea is that all these add-ons are going to be distributed in source code anyway. So so I think before actually showing the source code and how things work in code, let's spin up Unreal itself and run a couple of examples and see how it works. and and add a few comments about it, especially for people coming from Quantum C Sharp. And then we can go back to code and start doing some things and explaining how the whole thing works based on the topics we decided to show. So I already have the project open here. There's some source code showing up, but I'm not gonna open anything yet. I'm just interested in compiling this and running the editor so we see what we have. It shall be quick. We're using the binary version of the engine. So this is running on Unreal Engine 5.2. I think it's 5.2.1 if not mistaken, but any 5.2. So this is a demo scene we have, and so we have a bunch of Unreal blueprint actors that are derived from some C++ actors we implemented. Everything Quantum Unreal is done with regular Unreal actors. And there are some things that are totally optional or basically boilerplate plumbing. Like we have a demo menu here that lets you connect and start the game online and all these things. And this is of course not mandatory to be done the way it is done, but it is just a quick start for you to do things. And this test scene here has a few things that we will explain one by one. But for example, we do have an Unreal landscape, um, the equivalent of a terrain on Unreal, and it has already, we added to it the Quantum Unreal collider that extracts the data from the Unreal landscape and bakes into our deterministic physics for a static collider for the terrain. So we also have a few actors in the scene, like this sphere that's added as a sphere that does not move. It's just a collider. We have a couple of of um, of actors that behave as a physics body that they move around, and we'll be able to see that when you run, including one with a compound collider and a few other examples. But this is also going to spawn a character, and that's the easiest way to see things in action. I just want to, before even explaining everything, I want to disable the bug gizmo here because I don't want to see just the character. The first thing I'm going to do here is I'll just straight away run this because I know it already works. I think I'm spawning here two instances. Yeah, two instances of the engine running as two different processes so we can actually run online. But I'm not going to spin the second one yet. I don't know why my has this message with the landscape stuff. I can actually run it online. Let's see. And they will be connected so we can have them showing the same thing. Let's see if it, I'll just make sure I use the specific name here. But um, once I start this here, so this is actually the demo character controller that we built very quickly in Quantum, but using working on top of the Quantum Predict-rollback physics. It is using an Unreal demo mannequin, the Many mannequin, and perhaps this is one of the things we can comment and show, which is how easy it was to integrate the existing Many animation to extract the data from our character controller instead of the original Unreal movement control. But then, yeah, so this is all running over our physics engine and not Unreal's. So, and that means that if I join the second client, it will late join, receiving a snapshot of that guy, and I had a crash. So that's how live demos work on a preview SDK. So I'll just right away open it again and start over the whole thing. And so perhaps I didn't get the latest commit on the branch, but let's just spin this up again and I'll start it too right away. Perhaps it is the fact that I'm running this from a laptop and I'm opening the two clients as two separate processes. I also have OBS running, so it's a bit demanding on the CPU and on the CPU. So I cannot know for sure, but I'll just try it again straight away. I'll just start it right away so we can show working. I'm not sure I saved settings. I did save. Okay, so see the two windows. I just want to demonstrate this running in connected clients right away and staying in sync. Um, and then we can keep testing afterwards a single client because that consumes less resource. And yeah, it is running a bit that I'm not able to. Yeah, I'm not. I think I'm not gonna be able to demo this too. Yeah, I think I'm not gonna be demonstrating. I might be short on results. I will. I'll run just.
I think I can run here from my machine and
Yeah,
share
perhaps
screen.
that's an idea. So let's try that, Daniel. Before I'll try to fix here while you. So
Yeah.
switching to your screen. So if you can enable your screen share, we can
In a second.
remind to one. Yeah, I can run fine if it's just one. Um, I'll switch to demonstrate that while I have OBS open. So um,
Can you see both my windows?
I can see. No, I can only see the editor screen. So perhaps you should share the
Yeah,
whole desktop as you did before.
exactly.
Okay, so it is working for you, right? I actually
Yeah,
could make it work for me as well. So I'll go back to mine here and I can demonstrate better.
sure.
So I'm gonna run again and then so we start. So I have two screens here. Just making sure they're big enough so you guys can. Let's hope it works fine now. Just gonna select a different flash and guys together this time, although that's late joining. So no, I'm not. I'm being pushed by the capsule, but you guys can see that the screen sync, and this is actually running connected to the Europe region. So we have these two characters running in perfect sync here. I will stop and we can start showing how this all works. So I think I have a couple of comments coming from our colleagues at Slack. Okay, so nothing related to stream. Let's go back to this. Check. Okay, so now that we have all working, let's comment a few things here. So there's a lot to cover, but people coming from quantum unity, let's start with some similarities and some differences. So first thing, you have here also very similar configuration assets. instead of using Unity scriptable objects in Quantum Unreal, we're using Unreal data assets. And if you're familiar with Quantum, you have something called deterministic. So you have deterministic config. We call it session config or determination config. Um, it is a data asset in Unreal. We did not expose all the parameters that you have on Unity, but technically they exist here on a C++ class that's exactly the same data structure as the one in Unreal. In Unity, I'll explain why in a minute. But we expose the most important parameters that you can define the how many the maximum number of players you want to have in the session, um, the tick rate of the simulation itself, and all the expected stuff about the predict-rollback behavior and how input latency works starting at 0. So you start with input, it adds it if a client runs on high ping and so on and so on. So a few things that are similarities as well. So Quantum Unreal and Quantum for Unity version 3, which is the latest one that's also under development and being shared to Circle subscribers only, they share, for now at least, they share the same server-side code. So on the Photon Cloud, the game agnostic server logic that we have to coordinate input, time synchronization, configuration interception, and all those things, it is the same. So the same server plugin that we run for Quantum 3 C# version, the same one that we use here. Meaning that all the features that exist in Quantum 3, they are potentially existing here, but I'll mention the ones that do exist. So all the webhooks that were added to Quantum 3, they are automatically working here. So everything that you have on webhooks can be used here because it is already valid and available. If you create an app ID for Quantum 3, it works for Quantum Unreal, and it allows you to use webhooks. Second, yes, it supports up to 128 players simultaneously. So if your input struct is small enough, your simulation is clean enough, you can run 128 players just fine. And because of webhooks, etc., we also made sure to cleverly use JSON for the things that matter. So the equivalent of the player loadout called runtime player that we already implemented an example here. We did it with an Unreal F struct encoded as JSON because Unreal has great JSON support. So and then it plays nicely with the protocol that we defined for Quantum's webhooks. And finally, it comes out of the box with support for multiple players per client, dynamically added. So you can start the game and you are basically starting as a spectator. It doesn't matter if you started from the beginning or if you late joined, you are running as a spectator until you decide, hey, I have a local player who wants to play the game, and that's dynamically added, and then you gain control of a player, of being able to send input for one player reference. And you can actually send multiple of these requests, so you can have two players playing from one machine against one player playing from another machine, and you can mix and match. If you're brave enough to do this in Unreal, let's say, you can even have a mobile client with one player playing against two players on an Xbox and another player coming from a Nintendo Switch. So it supports this out of the box, and dynamically adding connect, and then you decide to add the player. So just like it was added for Quantum 3, because Quantum 2 already had support for multiple players per client, but you should decide the moment you connect. Now you can decide this after you connect. So these are similarities. Now let's talk about a few differences. And of course, feel free to ask anything. I'm just throwing stuff here as we go. Daniel, do you want to comment a bit about the differences in approach of Quantum C# that uses an ECS, a sparse set ECS, as the main programming API, compared to the approach we're using here, which is using Actors and ActorComponents. So please, can you comment about that?
Yeah, sure. Yeah, so I think before getting into that topic, I think one another worthy mention regarding similarities with Quantum 3 are input data compression. Uh, did you mention that?
I did not. Also because it is expected that we will have it, but right now it is not implemented
Yeah,
yet,
yeah,
right? But it will come with
exactly.
it at.
Yeah, okay. So regarding ECS and actor composition, I think that might be the biggest change in paradigm for the user from the user perspective there, especially the ones that are already used to work with quantum unity, because there you are already um, used to work with this very ECS style of gameplay logic. So you have your components, they're strictly or usually just data wrappers, data containers, and most of the logic runs on systems. While on Unreal, we embraced the Unreal actor composition model so that you can have both state, rollbackable game state inside either actors or actor components, and also have logic running on them. So it should feel very familiar to developers that are already used to working with Unreal, or even those that are used to working with Unity mono behavior and would like to transition to Unreal for testing or experimenting.
Okay. So perhaps we should show a bit of code, but before showing the code, I'm going to show an example here. So how does quantum work in Unreal then? Since we're talking about using actors, the way it works is the following. So once you start quantum inside Unreal, so you have Unreal running, you are an Unreal map level, and once you start quantum, what what quantum does, it scans it either has pre-baked or it scans the loaded map in search for certain actors that implement a certain interface. So you can start with some actors already. So say we're gonna have a few obstacles, a few physics objects that are already present in the map. So this is your level layout or something like that. So Quantum is going to scan this, and you're going to have them on all machines. All machines are starting from the same scene. Um, so Quantum scans and grabs these actors that implement a certain interface. And when they implement a certain interface, Quantum knows how to where the actually Quantum is going to initialize their live game state into its custom heap, but we'll show this in the API in code how it works. But essentially, these actors are part of the quantum simulation. You can have all other types of actors that are view only. So you're going to have your widgets for UI, you're going to have particle effects and whatever visual effects and lumen related global illumination and nanite for rendering meshes and whatever you want in terms of rendering. But some of the actors are going to be your game simulation, your game state simulation. So these are going to be some Unreal actors that implement a certain interface, and we're going to talk about them in a minute. We're going to show the code about in a minute. But you can also dynamically spawn and despawn um, actors that implement the same interface, meaning that they contain game state and they can contain predict-rollback logic. Show both how you define game state and how you implement logic using this. This interface can be implemented either by actor, an actor class, or via an actor component as well. So Quantum is agnostic to where is you put this in actors or actor components, as long as they are contained in actors that implement one. A few other mentions. This fully supports the editor inspector for so let's say we define one specific actor class that implements this quantum interface with some game state on it. But then you have your level designer that's going to specialize this as a blueprint class. This is all supported, and you can define all the view rendering stuff, animation triggering, everything can be done in blueprints. We think that the right pattern here is to implement gameplay in C++, at least the simulation gameplay, but use blueprint as much as you want in terms of triggering animations, controlling VFX, spawning things, and we're going to show a few of these hooks, a few today because it's a lot. We have a lot to cover, but we'll show more as we go. So in this example here, so this test KCC 3D blueprint here is a good example because it is so this is a blueprint class that extends this class called Quantum Basic Character Controller 3D, which is in source code, and we'll show how it is and what its interface. So it's just a blueprint class that extends that, and it also so it has some stuff that Quantum is not does not know about, like the spring arm based camera, so can follow the character. It has an animated skeleton mesh, but it has also the quantum transform. We can talk a bit about. Daniel, do you want to talk about what's the role of a quantum transform, which is an actor component? So how does it work when you have an actor that has a quantum transform added to it?
Yes, of course. Yeah, so in quantum we used fixed point numbers, right? Because fixed point math is deterministic. So the quantum transform is the quantum equivalent of your transform component that exists on Unreal. So when you add a quantum transform to an object on the scene, that object bakes the Unreal transform data from float point numbers into fixed point numbers in editor time. So you have that entity that actor prototype in your scene that is spawned when the game starts, or you can also spawn actors on the go, of course. And the simulation works on that transform, and and we do some scaling back and forth to work well with Unreal's centimeter scale. While on the simulation side, we use meters because it's better for the range of the fixed point numbers. And so you continue to visualize all the visual effects, animations in, let's say, the Unreal floating point realm, while the simulation works with the
Let me
quantum
show that.
transform fixed point data. Yeah,
So we have Corium settings here under game, and we have that called bake view scale. I'm showing that on the screen, so you can continue.
yeah. So basically, Unreal uses centimeters as distance units by default, right? While fixed points, yeah, a better range for fixed points are meters, because when we start to get into very small scale with fixed points, it's when precision starts to become an issue. So we pre-build this baking view scale where we convert back and forth your Unreal data into fixed point and back to Unreal floating points when you want to visualize things. So this allows you to more easily adapt your maybe an already existing Unreal project that was built entirely using centimeters, and you don't need to worry about changing the units of your game. But if you, it also supports if you want to use meters on Unreal as well. That's a configurable
Just change
scale
that
that
scale
Eric
to
just showed.
1.
Yeah,
Yeah, you just change that scale. I wanted
exactly.
to comment on that showing here visually because so we have this sphere collider here, which is just an Unreal actor. It's actually a pre-built actor class that we called Deterministic actor that does nothing. It just exists and implementing the interface without any game state. So it can be picked up by Quantum when it starts, but otherwise it is a regular actor. And so this actor here has an Unreal mesh renderer, but it also has a quantum transform. And what I want to comment is about what Daniel just said. So if you see here, so the Unreal transform has 280 centimeters, 360 centimeters. So this is a centimeter scale um, position. If we see the quantum transform, fixed transform component here, you would have the data baked into meters. So you have the approximate here 2.799999 meters, which is 2.8 meters, and 3.6 meters instead of 280 centimeters. And this is done automatically based on that baking scale that Daniel showed. So this is the baked transform. So essentially you place it on the scene and you can move it around using the Unreal Gizmo normally. And once you save or enter play mode, it's going to bake the data. And when Quantum starts, you will use the baked data into the transform. But then in runtime, so this is the new positions based on the change I did. But in runtime, you actually change the position of the quantum transform, and then the visuals are going to be moving accordingly because this component does that for you. It is given in source code, so you can take a look at how it works. Um, this also has a fixed collider added to it, but I want to show another one here, and then you can comment on it. It's capsule body here, which is again another basic basic actor that just extends deterministic actor, let's say the placeholder empty actor that has a static mesh for this, I think it's a capsule in this. So take a look at it here. It has a capsule mesh, but more importantly, yeah, so it has a capsule, some other stuff in here, to get to simulate the visuals of a capsule. But what I wanted Daniel to comment on is that these three different components that we have here, because these are pre-built actor components that we ship with the SDK, and you can use them very easily. Daniel, can you comment on this? So we already talked
Yeah,
about the transform. Now we have a collider, a capsule collider 3D, and a physics body 3D.
exactly. And these are the, let's say, building blocks for those of you that are used to quantum unity. There are building blocks for quantum physics, right? So you have a transform and a collider for any physics enabled object, and optionally also a physics body component. So the collider can define if the collider is trigger or not, and in Unreal terms, if it blocks collisions or not, and different shapes. And we are already supporting capsule shapes on Quantum Unreal, as we are also doing on Quantum 3 for Unity. And with a physics body component, you can specify either a kinematic or a dynamic physics body with mass and all the rigid body physics settings of including physics material, and define callbacks. So for the define layers. So for the callbacks, we are using a similar approach to Quantum Unity, except we are
Daniel, can you
using.
stop? Can you
Yeah.
stop a bit more? So let's. I think it's nice if I show what you're talking about. So
Yeah.
let's start with the collider because you talked about the transform a bit already. So here's the collider. I'm opening here. So we have the collision, we have the capsule collider data with the local transform. Yeah, you comment about the capsule collider in general. I can highlight what you're talking about.
Yeah. So we support shapes, different shapes with local transform offset relative to their transform component, right? We You can define callback flags. So for those of you used to Unity terms, which we call on collision and on trigger, on Unreal we call hit for blocking collisions and overlap for non-blocking collisions or trigger collisions, right? So you can define exactly which callbacks you want to receive. So I want to know when my character enters a trigger area. So I would enable the on dynamic begin hit on dynamic begin overlap. So I receive that callback exactly once when the character enters that trigger area, and this is deterministic and rollbackable. So if you predict the character entering, you would see that callback during the prediction, and if that movement was confirmed during the verified frame simulation, you would also receive that callback during the game simulation. So it works with the way quantum expects it to in prediction rollback. And yeah, you can define trigger areas for blocking or non-blocking collider, define physics materials, which are material assets, data assets similar to Unreal physics materials, and we use the same nomenclature, the same range of values, so that if you're already used to Unreal physics materials, it would be very familiar to you from the get go. Um, so yeah, so this is the collider, right? And the physics body adds some utility, some dynamic rigid body um, logic on top of that. So you could have, for instance, a kinematic body where you set in your KCC, for instance, if you want to move the object manually with your KCC code, so you could have a kinematic collider by adjusting the flags on the body. Define drag coefficients, gravity scale, so per object gravity scale. Dislocated center of mass if you want to have an object that doesn't have the center of mass exactly at the centroid of the collider. And we are also building different inertia modes to make it easy to configure inertia in different objects, which is something we realized was very useful, especially if you're handling vehicle physics, right? So you want to have this fine-tuned control over the inertia of a vehicle of a more complex dynamic body, so that you can um, have full control of how it reacts to
I'm
your
showing
steering input or a ramp.
I'm showing the parametric way of defining inertia. So I'm defining the
Yeah. So
inertia
the
of this capsule
parametric.
body as a box that resembles this yellow thing. So then you can comment on what that means.
Yeah, so essentially, you by default, the physics body inertia takes into account the mass of the body and the shape of the collider, and it assumes a uniform mass distribution over that shape of the collider. Right? When you configure the inertia from a parametric shape, you're essentially saying please disregard my collider shape and take this box into account instead. So the inertia will be computed based on the mass of the object and the parameters of this box, of this yellow box you are defining. So if you want to emulate that your vehicle or your collider is more elongated than it actually is, you could change only this parametric box to then have the inertia based on that. And we think that is useful because it's usually computing inertia manually is usually tricky and a bit complex. So most people don't want to go into that. So we want to expose easier ways for you to tinker with that, because it's very important for some games, and we want to empower developers to have more control over the dynamic behavior of these complex objects when they need. So that's a nice addition that we also want to port to Quantum 3 for Unity, just because it's a very nice thing to have overall.
Yeah. So let me take a look at what else we have. So this is a good comment, but I think you should also mention that when you run quantum here, it's our physics engine that's running, our fully deterministic, predict rollbackable, stateless, soon to become stateful, but stateless physics engine um, running for prediction and rolling back. It's always what you see is what you get. You don't have delays on physics reactions and all that. So you can comment about that. That's not using chaos physics, is using our physics.
Yes. Of course. Yeah. So our physics engine, we're porting it to native code, and we're calling it now Corium Physics. And this physics engine is our battle tested quantum physics that was used for quantum unity in C sharp, but ported to C++, right? And It's, as Eric mentioned, stateless, deterministic, rollback capable physics engine. Um, and when we run Quantum Unreal, it uses that physics engine in the lower layer of the simulation. So all of these fixed components that we showed, fixed transform, fixed collider, and so on, they are defined by the quantum physics, and they are interpreted into they're used by the quantum physics in runtime, right? So everything that you configure on these objects are gathered by the physics engine, and an update loop is runs every prediction or every verified simulation. And the nice thing about it is that we can now have only one physics engine source code, right? So if you guys have been following our development progress on Quantum 3, you know that Quantum 3 uses already this hybrid physics engine where part of the tasks run in native, even when you are running Quantum Unity C# code. And we want to have this unique physics engine that fuels both Quantum Unreal and Quantum Unity, because it makes easier for us to maintain um, and add new features and fixes and improvements on the go, because we have this single code base that it makes it faster for new features to reach both Quantum for Unity and Quantum for Unreal. So yeah, so everything that you would expect from a basic from a physics engine that you have on Quantum Unity is already ported here. We have queries, we have raycast, shapecast, shape overlaps, dynamic collisions, islands, sleep detection. We are porting GJK for support to continuous collision detection, and also porting the support to broad phase queries, which is something kind of unique to quantum physics, where you can pre-inject queries to be resolved on the go, and they are much faster than regular queries are.
Let's
And so yeah,
I would like to show a few more let's say interesting features that to program, and I want to also soon move to showing how game state is defined. So I switched the spawner here, Daniel, to spawn a vehicle instead of the character. So I'm actually driving that vehicle. So it shows the there is some clipping going on here because I think the landscape baking is a bit offset, but we can leave it. Um, what I want to move on to is a few, let's say, more generic topics about it. So one thing I wanted to mention is that in quantum C sharp, we have this concept that let's say if you're running the simulation at 60 hertz, because you have this is running at a fixed step, it's not even if you're rendering Unity as at 60 ticks, 60 hertz as well, the ticks are not exactly going to align because the simulation ticks they have to run with the server clock. So they may alias with the Unity one, and for that reason, the only way for the view to look smooth is to interpolate between the two last frames. So you're normally viewing stuff one tick behind. And we decided to experiment with a different concept in Unreal called partial tick prediction. So everything you see here is it's running really to the rendering rate because we simulate the fixed step ticks, including the prediction all the way to the last one that we can simulate the full tick. But then we call one extra tick for prediction with a variable delta that you receive this parameter. And we're going to show next thing we're going to show now is code finally. So then you have this partial tick prediction, meaning that the thing is actually constantly extrapolating to the rendering time, not only to the latest complete tick you can simulate and grab input. It really renders snappy to the rendering. It really simulates snappy to the rendering, meaning that you do not need to have interpolation. You actually use simulation extrapolation to the last millisecond. And of course, It's possible to use normal interpolation like quantum unity, but by default we have this partial tick prediction. I think we should move to code, start showing how you actually define. So how do you create game state that can be rollbackable? How do you define this? How that does that? Can you make it show in the editor like we showed here? Let's show how these options work. I'm gonna close the engine itself, saved everything that I modified, and just then we can take a look at the code. Yeah. So where do you think we should start?
It maybe show how you can define a Q-replicated, quantum replicated state on an object,
Okay.
on an actor or actor component.
So let's choose one here. I think so. I will start with an actor. Let's say we have an actor that we want to have game state defined into it. I'm not gonna open the vehicle one because that's massive. That's a bit bigger than necessary to show. So I think I will start with the player spawner because I think it does have replicated data to it. So let's take a look. Also, it shows the concept of runtime player and runtime config, but I do not want to touch on those yet. Um, so the quantum player spawner is a subclass of deterministic actor component in this case. It technically did not need to actually inherit this class. It could just implement the iQuantum object interface. But I think when I first coded it, I did it like this, and both are same in this. So, but it could be, so you either inherit one of the pre-built empty classes or you implement just the interface. But in this case, it is a component and it's inheriting the base empty class that we have. Um, and there is one mandatory thing which is similar. We use the Unreal header to code generate a lot of the boilerplate stuff for you. So you see that it will feel very similar to regular Unreal because things are basically U properties like regular Unreal stuff. And because there is some code generated bits, there's some macros and some patterns you have to follow for that. So in every header file, you have to add one line for including the generated header that we create with our extended header tool. So this is a regular Unreal Engine. It's not a special Unreal Engine version. Everything is done with the plugin. So we have an extra Unreal header tool extension that does this plumbing if you add these things here. So what we're doing here, so you add this, that will be the generated part that we do, and you have to add this macro here with the name of the type you find. So this is gonna do the plumbing for generating the stuff. So let me take a look if we're actually doing on this particular actor component, if we're doing any game state with. So this one does not have game state added to it. So it's, oh yeah, it does. It does have one game state added to it, 1 point of game state, which is not really being used. It's just for demonstration purposes. So I think we can modify it and show it how it looks on the editor. So this is a regular Unreal component that is aware, or Quantum is aware of it. But the only thing that's actually being used here are these two callbacks called onInit. That's called when Quantum itself starts, and we have this onPlayer added here that is called when one player connects. So I'm using this to actually spawn the characters for all the players on the local deterministic simulations. But it's not actually ticking, doing any per tick gameplay logic, rollbackable logic here. This particular one. So maybe we can add these things to this one as an example. But it does have one rollbackable game state that I know I'm not using, and it has some read-only data that is used. So for example, I defined this reference to a blueprint class here, basically to tell the logic here what should be the class I should spawn for one player when that player connects. So this is what I used on the editor to define, hey, please spawn this truck to every player that connects, or spawn this character here. So that's what I was changing when I from running with the player character or driving the vehicle. It was actually changing on the editor the blueprint class that would be spawned by this. But this is read only here. It's just read by Quantum to dynamically spawn an actor. But you can actually have game state itself that is rollbackable added to any of these actor or actor components. And then you mentioned something called queue property. So there are three ways for you to define game state that is rollbackable in a quantum actor or actor component on Unreal. So the easiest way is to use the macro called queueReplicate, which lets you define the type and the name of the property. I forgot what the order is. I can just check a
I
more.
think the quantum basic character controller might have some example of that.
They all have. I think the yeah, this one has. So yeah, it's type and then. So queueReplicate is an interesting one. So I'm gonna say here I want to have a f fixed, which is our numerical deterministic type that replaces a float number or a double number. So this is the type. I want to have an f fixed type, and I'm gonna call it my timer, whatever it is. So queueReplicate, the macro. This macro is the easiest way for you to add game state. Let's just see if this compiles fine, and I'll explain what this does. So when you add a queueReplicate, it creates a property, sorry, variable, a field inside a generated struct. So let's go back a bit. So for every actor or actor component that implements the quantum interface that has game state, we generate I struct, an F struct with all the game state that you defined that you want it to be rollbackable. It is important that this is done on a separate type because this type will be allocated in our own custom heap, not into the Unreal garbage collected heap and so on. So it is stuff that we allocate, that we control the mem copy, and we deallocate when necessary, very high performance. So we generate this type. So all the properties that you're going to add that you are going to mark as rollbackable are actually generated into this type. So we'll see on the API how you access them. And the easiest way to define a field to go into the rollbackable game state is to use queueReplicate. QReplicate basically adds a field called timer. In this example here, it will add a field called timer, and the type of it will be fFixed, which is our fixed point number. I compiled it, it works. But this one does not generate editor code for it. It is the quickest way for you to generate game state that exists, is rollbackable. It will always be initialized as 0, but you can modify it from gameplay just fine. But it starts as zeroed. It's always zeroed at the beginning. The way for you to define game state that you can, as a level designer, as a game designer, you are able to type in, position, bake in initial data to it, is to use the second method called queue property. So a queue property, it's basically an Unreal U property. It accepts exactly the same parameters as the U property that you may be used to or used to using Unreal. And let me just check. I have messages from our colleagues. Okay, nothing related. All good. So it is same as Unreal U property, but it tells Quantum to use it. But there are a few gotchas here. So first one is that because it's a U property, the syntax is the way it works is the same as a U property. You as a macro before the field, and you define the type, then you use the name followed by prototype. because this is going to be a regular Unreal U property that exists on the actor or on the actor component. It is allocated here normally as part of the Unreal type. And this is what lets you type in and save data. But this data should be treated as read-only in gameplay. It is your prototype values for these. What Quantum will do is we will create a field called player in this case into the same type where it has a timer. The type of it will be an integer. And what will be the initial value of it? If this is a map object, it will be the initial value that comes from the baked map data there that will be baked here that you set in the prototype. So that will be the initial value set to this. But then you can modify the live version of the type on your gameplay code. You can use any type that will be deterministic. We have all the numeric types, vectors, quaternions, collections. We'll have to do a second stream with more detailed things, but there's a bunch of stuff you can do. So this is the second method. So QReplicate just creates the field. You do not do any game design, level design. Initialization is always zeroed, but good for non-exposed properties. The one that you expose with Q properties, the one that you let level designers create initial values, that you can have several variations coming from different blueprint subclasses that have this component or not, each one with its own values. And the third method is a more complex method in which it lets you define an F struct with your whole game state that you want to have for an actor or actor component, and it lets you say, hey, for quantum game state, I want to use this F struct, and that's it. You don't have to define individually the Q replicates and Q properties things. You just define an F struct using regular U properties, and you say this is the quantum game state, the whole struct. So it lets you mix and match these three things. I mean, well, the struct version is just that, but it have these three different options to do. I before going back to the editor, because we've seen a lot of these, how these are exposed on the editor, like fixed point numbers looks like a float editor inspector. I want to show how this actually looks like in code. How do you manipulate these? So I'm gonna open this. This is the header file. I'm gonna open the CPP file for the same class. So quantum player spawner. I'm gonna skip a bunch of stuff because again, there's a bunch of people watching the stream, but I don't have questions. You guys can ask anything. So if you see something that's kind of interesting or weird, just ask. We can comment about it. But I'm gonna just comment on the topic I'm talking about, which is, so I said that these two things are gonna be co-generated into a type. How do you access this data then when quantum is running? So in any component or actor component in Unreal that runs in quantum, it will have a pointer called QState, quantum state. And the QState is going to be a pointer to the struct that's code generated by quantum. And where does this state lives? Into our heap. It's fully rollbackable, but you don't have to worry about it. Once it is initialized, it's always the same pointer. When we roll back, the data that's there will be rolled back because the heap is rolled back. But the pointer never changes for you. It's the local pointer. You always have access to it, so it is easy to work with it. But it always is always named QState. So this is the name of the pointer. And what data will it have in it? So IntelliSense, although it's a bit slow in Unreal, it already I took enough time, so it has here already player and timer, which are exactly the two properties that we defined. So this is the only data that is rollbackable on this particular actor. It's the player, which is an integer, and the timer, which is a fixed point number. So you can whatever you want. For example, I can set a fixed point number as an integer because it accepts that, it casts that finally fine. You can also use any of our Corium fixed math const can also use any of the pre-built constants that we have that are very useful. So I have something as 0.5. So we have a pre-built that. So initializing it as that. So um, but yeah, that's how you access rollbackable game state. Quantum state are fields. That's all. How do you implement predict rollback code then? How do you do your how can many questions I can have. So Daniel, can you ask a few questions? Or some of our guys can ask any questions. Then I can show some stuff.
Yeah, I think the first question that would come to mind in this use case is then how would I increase my timer? How
Okay.
would you do
Yeah.
to increase your timer every tick, every frame?
So how do you do that in Unreal? I ask. You're an Unreal developer, Daniel. So how do you implement gameplay in your actor or actor component?
So I would increase a float point in my tick method. So the one
So
that's
Unreal
called
has
every
something called tick, which is a method that's the equivalent of Unity's update. So for Quantum, you have something called Deterministic tick. But this guy receives a special parameter. I'm gonna open the another example just to copy things. Oh, let me open character control, which is slightly less common. I have a bunch tick. Oh yeah, it's public. So you implement a method called tick, a deterministic tick. It receives something interesting called tick info. Let's implement this guy at the right CPP, and then we'll see what it has.
I think it's worth saying that we are taking this approach with many of nomenclature that like adding the deterministic prefix to most of our stuff, and then using the names you would expect when working with Unreal. So deterministic tick, deterministic actor, or deterministic hit callback. So it if you use something on either deterministic or fixed. So when we have like the corium or the quantum equivalent to a transform to a collider, we add but using fixed numbers, then we use the fixed prefix or fixed transform, fixed collider, and so on.
This is a
So
convention,
I
at
think
least on the preview
yeah,
SDK. Of course, we may change depending on feedback, and but for
yeah.
now, it looks like we're gonna stick to. So I wanted to comment on the tick info. So this is the equivalent of a real tick, but it's also the equivalent of Quantum C Sharp. Is the equivalent of the system update. But in a system update, you receive the full game state as a frame variable because it's an ECS. Here you have access immediately, of course, to your quantum state uh, pointer, which has those two things, player and timer, that you can increment your timer somehow here. But how do you increment the timer? So how do you get the delta time? So that's where you get tick info. So you can say, hey, my timer is going to be incremented by, then you get tick info, which is passed by reference. Then you have something called delta time. So that lets you increment your timer, and delta time is a fixed value, so it's a fixed point value. So this is the equivalent in Quantum C Sharp of frame.delta time. Receive an update, you have the delta time here. But tick info has a lot more stuff, so we added a bunch more stuff to this guy. So it has the delta time, it has the input for all players, it has some booleans telling you if this is the last predicted tick you're gonna have, if this is the predicted previous one, which is gonna be the second to last. It tells you if this is the very last extrapolated tick, for example, for partial tick prediction. It lets you know all these little things. You know the tick number. This is the equivalent of in Quantum C Sharp frame.number. So this is a sequential number that you always have, but of course in rollbacks you have these numbers are rolling back and resimulated all the time. You have the total time, and I also passed. We decided to do this. It's the variable update rate because of this partial tick prediction. You cannot just use the update rate to update stuff if it's a partial one, because sometimes you want to use the update rate instead of the delta time because it's more precise to use the integer number on those cases. But in case of partial tick predictions, this breaks because you cannot just use the fixed update time. You can if you just do on the complete ticks, but not on a partial extrapolated variable delta time one. So we compute what the equivalent of the variable update rate would be on this very tiny tick that is simulated. So you have this pretty big update rate number that you can extrapolate things with when you have this very tiny update. So it's all in here. You know if this is a verified or predicted tick by checking this verified. So you know, oh, this is the final simulation. So this is the equivalent of Quantum C Sharp's frame.isVerified. We didn't add a is predicted, but that's the opposite of this, either predicted or verified. And the partial one is a predicted one that is the last one, that is the extrapolation one with a tiny delta time. So that's what we add in tick info, including the player input and a bunch of other stuff. But so this is to answer that question about how do you uh, implement gameplay logic on a tick by tick basis, just like this. And this is magically gonna roll back the game state for you. You don't have to worry about it. It's always rolling back and resimulating, eventually simulating the verified one. Um, you just implement this. You don't have to think about netcode. You add forces to physics objects. But then I have a question, Daniel. I'm going to ask you to answer that one. So in Quantum C Sharp, you have the concept of a frame, which lets you have access to the whole game state from the simulation perspective, from the simulation updates. Here, I only have this actor component and this tick info thing. So how can you access? Of course, you're going to add a few more APIs, but how can I access the relevant game state for me from this particular ticker here?
You
Can
mean
you
the
give me
state in another actor?
yeah, something like that? Can you give me a couple of ideas? Of course, I can access my own queue state that belongs to my
Yeah.
actor or actor component, but how can I have, for example, a character know about a weapon that he carries? Or of course, if it's a component inside the same actor, you can use default components as part of your class that come with it, so you have already the pointers to them and so on. But I'm talking about grabbing access, discovering about other actors. You can think about overlaps, for example, but how do I keep references to these things and do this in a rollbackable deterministic way? I'm gonna fix my lights while you answer.
That's actually a good question. So you can have a reference to another actor or an entity in this case, but in this case it would not be rolled back unless it's part of your game state, right? And so you could have what would be the equivalent of the entity ref on Quantum C Sharp?
Yeah, that's a good way to think. So how would you keep a reference to another object? Of course you let me just check if we have questions here. No, it's another topic. Nothing coming from our team. So let me comment on that. So of course you can do an overlap and find the references to some actors that are close to you, but the right way to keep a reference is just like you would do in Unreal. So you can store a pointer to another actor. And storing a pointer to another actor, so the quantum game state supports uh, storing a pointer to another actor. And that is rollbackable. It's also it's also serialized for late joiner, so all this can be done. So essentially, you can do something like a queue replicate here. I think it is T uh, object object yeah type. I'll give an example of a specific type here. Let's say a deterministic. Let's say a character control type of our character. I'm not. Yeah, I think I do have access to the header of it. No, I don't. I didn't. So I don't wanna. I don't wanna couple things too much here. So I'm just gonna stick to this for now because. But if I had access to the if I had added the header to the character controller, I could make this pointer specific to character controller. I'm gonna do it just a pointer to another deterministic actor, and I'll call it other, whatever it is. And let me see if the syntax is correct. And so I'm using an Unreal soft point here, and this is supported both for rollbacks and for serialization for late joining. So it compiled fine, and the way this, so it will be part of our queue state now. And come on, my IntelliSense takes time, but I call it other. What? Yeah, for example, I think this file. So or maybe I should do this. I can do this when I spawn the character. I can keep a pointer to the other guy there. In that, let's not set it to test if it see if it exists and compile. So it does exist. So I have here on add player that I actually keep. Let's keep a reference to the. Oh no, this is not this. Is the I want actually to player added when I spawn the actual. Yeah, here's where I spawn the actor thing, which is if we pay attention here. So we have this thing subclass of a deterministic actor called player class. So when we spawn this guy, it's definitely gonna be an a deterministic actor subclass. So we can assume it is. We can force the cast here, so we can do that our other queue state is equals to in I think what is this? So so queue spawn actor returns not the generic type but returns actor. So I'm gonna do here queue state dot other equals cast to a deterministic actor, and this will work. So then I keep the pointer here. So the last one that is spawned would be kept as this thing. If somebody late joins, the snapshot you're going to receive is going to contain the pointer to the last one that you receive, but it will be the local pointer you have on your machine. So this plumbing is all done for you. You don't have to worry. It's similar to replication netcode in that case, the case of late joiner. So for anybody coming from Quantum C Sharp, this is kind of going back game object. It is the Unreal way of doing it with actors, so we didn't go for an ECS. Although performance-wise, this runs. So rolling back and predicting this all is very, very, very efficient. So the number of mem copies of the game state we do is very, very minimal. It is based on the size of your game state, and it's done with a fixed number of times. We don't do based on the number of predictions you do. And every time you access stuff, the pointers are kept the same. We just change the contents of the working heap, which is the heap you have access to from your point. And so everything you do on queue state is always rollbackable. Um, Let me see what else. So that answers the question about how you keep access, how you keep how you keep references to other objects and so on. So you can predefine these, you can spawn and keep a reference, you can set them. We're gonna add a few APIs for you to query the quantum game state only, searching for subtypes of a certain class or For example, I wanna have all the instances of a deterministic vehicle subclass, something like that. So and we'll make sure that these are fast because Unreal has the iterators for you to grab in the actors, but we want to have the specific ones for quantum added with as to be as performant as we can do. And we don't have this API yet, but we'll add it soon. Um, and this is another way. But of course, if you do an overlap query and something, and you grab a pointer to something, you can directly do something with its game state, queue state right away, or you can also keep a reference because having points is also valid to add to the game state. So let me see what else we can comment on, Daniel.
How would you go about like changing something on the UI based on your timer, for instance?
Oh, that's a good question. So I think it's a good moment to change to the character controller and show how we do the animation on the character controller and how I was able to reuse the animation blueprint that comes with the pre-built Unreal Many. It's called Many, two N's and Y. Demo skeleton animated uh, actor. So a blueprint. So let me show then the interface of the character controller. We can close this spawner. So the interface of the character controller. So it's a bit more involved than that spawner, but it has a bunch of view properties like oh no, this is the config, the data asset that is the character controller config, character controller query. What matters is this one here. This is the actual character controller, which is an actor. So this guy, default component of this form. Um, this guy really needs the player prototype because I need to know who's the player who's going to control this character. So I need a player ref, which can be cast to an int. So I'm just using an int to know, okay, this character is being controlled by this player. So this is what I keep here. So I can grab its input and use that to move the character. But um, I have a pointer to the config, which is a read-only thing that I use. It's a real data assets that I use just uh, to know the parameters to run the character with. But what matters is these things. Yes, these are the properties of the character controller from the perspective of quantum, of simulation, predict-rollback simulation. But that's not what I'm interested in. So this is going to be running on ticks and predict-rollback and actually moving the character. But how do you use those things, to animate the character correctly, like we saw when I was playing with it? So I added a bunch of functions. So Unreal functions that can be accessed directly from blueprints. So I'm going to use these to read the current state of the character controllers. This is very similar to how the Unreal movement controller works. So the movement controller component exposes a few U functions that you can read from, you can execute and get the value of them, the return value of them from a blueprint to then feed that into the animation control, and then that's going to be used to move, control the blend trees on animation. So I basically replicated some of the stuff that was used on the original one using our numbers in this case. So we have the velocity, which is direction vector of where this character is going from. What is the acceleration this guy's moving right now? Um, I have a boolean saying, am I falling or not right now? Am I grounded or not? This one is not, this get player index is not used by the animator, but I also have it here. But this is the stuff that I'm interested in. So these things here, because they're similar to the stuff that is used, the regular Unreal character movement controller. So let me show the implementation of them very quickly. So get velocity here is essentially, yeah, if I don't have a quantum state yet, meaning that what should I have? So this is an interesting one. So when we're, for example, editing a blueprint, that is an instance of this actor running in the editor process, which is an instance of the Unreal Engine. So if you're familiar of how an Unreal Engine works, that's how the editor works. It is an instance of the engine itself with a different class implementation of some of the things, but it is essentially an Unreal Engine running. And but Quantum is not running inside the editor unless you're pressing play, at least in the default stuff. So we would not have the queue state initializer. So what I have here is I have a check. If this quantum state is in a null pointer, I do not crash. I return a default value here. Why? Because this lets me play around, and I could, for example, use a fixed U property if I want to configure this, because I can then test the animation directly in the blueprint editor. We're going to test this. So when we open the blueprint editor, we're going to be using this default value here instead of the live one. But if it is actually if it's the character, if the velocity is actually the character moving, we just return the actual velocity. So the Q state velocity. If quantum is running, we return the velocity. So acceleration, same. We have, I think this is not, I actually do not use acceleration as part of the rollbackable game state, so I created a temporary variable that's always updated from the last simulation, and that's the one I'm going to use. I just cache that and return. And falling state is essentially I'm grounded, or I'm not grounded, and my velocity is negative and bigger than a certain threshold value. So I cannot, it's just, I let it, it's not just smaller than 0. I decided to say I'm falling only past 0. Minus 0. Perhaps I should have used 0. But anyway, um, so it's just reading the values of the game state, uh, quantum game state, and then that's going to be used in the editor. Let's spin up the editor and see how that works. How that's used to spin up the animation. I'm reading. I'm not modifying from these. I'm just reading the latest version of the data that comes from the simulation and the Q state here, and I'm going to use that to feed to the animation. So I think I have here on character controller. So let me show this here. So this is the Unreal Many skeleton animation controller, and I actually reused the animation graph as it was. So I didn't modify any of this here. So essentially it has the falling variable and a few other things. What I did modify is that instead of having a variable for the Unreal movement controller, this guy's gonna be aware of a quantum character controller. So we have this variable as default variable. But this part here, which is the animation graph, is the default one. I didn't change anything. It's just a regular Unreal animation. And then the event graph is also mostly unmodified. I'm just going to change the source of the numbers to come from the quantum character controller instead of Unreal controller. And I'm going to show how that works. So we get here the blueprint initialize animation event, and then we get the owning actor that owns this animation, which is this is the default behavior, but we cast it to a quantum character controller, not to an Unreal movement controller, because we have this, and then we set it as the variable that we have access here. But bang. So this is done once when the animation is initialized. Cast the actor. We know this actor is going to type. Cast it to that and set it as a variable. So then every time the animation is going to be updated from Unreal stuff, what I get is I check that this is I get the character controller itself, checking if it's valid or not. And once it is valid, I do this sequence of things here. So first thing I do is I set the velocity. And how do I do that? I get the velocity, um, which is value then. I think I'm returning it as I forgot to comment on that. Yeah, I forgot to I forgot to mention it was here and I forgot to comment. So this does not return the f fixed velocity. It actually returns the unreal f vector, which is already the double or float version of value. And this is why I'm actually using 100 here on the default, which is 1 meter per second. But here I'm using this, I created this function here, to vector, because what it does, I think it's implemented here in this case. Yeah, it's just using the settings, the bake view scale settings, to convert from meter to the scale that's used for the view here, so it does not break. And it's actually returning already the float value, because that's what allows it to be here with the original stuff. So the only thing that is different from the original animation controller is this node here. This node get KCC velocity instead of the original get velocity that comes from the movement controller. And then I feed it into these things, which are exactly the same as before, as the original stuff. Didn't change them. Same thing goes here. So is grounded is essentially the original. I replaced with my grounded instead of the original grounded. And this bottom part here is unmodified. It already uses the velocity that was set here, the horizontal part of the that was set here. And last, same for is falling. I replace it for my is falling, and the set does it here. Done. Everything else uses the original. I just replaced the source of these three values in functions that come from our character controller instead of many of the original Unreal's movement controller. So that was it, and then this animation works. And the interesting stuff is, um, this guy does not have an owner because this is just the animation controller. But if we open the actual blueprint of the character controller itself, see that it has a test. It's a test KCC, the actor itself. The skeleton mesh uses as animation controller the mini quantum, which is that animation controller I was editing before. So that's essentially it. The rest is rendering materials. And if we open the viewport here, you can. I thought you that 100 value instead. This is the transform part. Expected this already. I will not bug this. But that's essentially the. Let me run. Let's run again just to see this in action. Oh, I have to change my spawner. My spawner currently is a truck. I want to spawn test CC, which is the class that we editing. That's also done via. So the camera setting and everything is done via Blueprint. I'm not. I know that right now. So here's the character. So all this walk animation, all this, and the speed at which it is. This is all based on quantum character control. See that it has the falling animation triggered correctly. Of course, you can make this complex and make sense, but this is normally game specific. But as I said, we're going to be improving this character control itself, the basic one, a lot. It will be source code, and we'll have a few samples. Daniel, do you want to just do a quick review
Yeah.
of the rooftop robbery? What is the name of it? What?
So extraction sample, extraction brawler.
extraction brawler sample. Yeah, can you take a
Yeah,
can
so
you
we have
show
two
it?
samples as Eric mentioned. One is the showcasing the vehicle physics, and the latest one is this extraction brawler. I think I can show here.
Yeah, let me know when it's ready, then I can switch.
It's ready. I think I'm ready sharing.
Yeah, so we can already yeah, and we have audio as well, which is cool.
Yeah, nice.
Just play with one.
So
It's show later.
it showcases the carrot controller. This is the 3D carrot controller. You can use physics queries to identify other objects, grab them. The objects are turned into kinematic objects who are being grabbed. So your objective is to place the money bags here in the extraction point. The cops are trying to recover the money, and they can hit you,
But you can
and you
also
can hit
punch
them
them.
back. Yeah, and throw things at them. Um, yeah, so your objective is to put the money bags there at the center and press R to start the extraction before, and then protect the money bags before the cops take them off the extraction point. I got busted. I don't know why.
I think
So I
it's because when
KO'd.
you I think it's because you extracted 50,000, and I think the final screen shows game over, maybe. Yeah.
Yeah, maybe.
Yeah.
Yeah, but yeah, but it showcases a few things related to physics, like dynamic collisions. All the money bags and boxes, they are these dynamic objects. It uses queries a lot to both identify that the objects got into the extraction point and identify, like, check which objects are in front of my character. Um, and yeah, it uses physics callbacks. It uses most of the dynamic shapes and static colliders as well. All the animation logic and visual effects, sound effects, the event system.
Yeah, it uses
These
quantum
are
event
all.
system, a bunch of stuff that we did not show.
Yeah, yeah. I think this sample, it touches each and every aspect of a basic quantum game. On some topics, it goes deeper into the features used. In others, not so much, but it touches everything. So I think it's a very nice um,
I'd like to
sample
mention
to
that this
to get
sample
into.
was developed for us by Dreamloop from Finland, studio from Finland.
Yep.
So thanks a lot, guys, and guys will hear them more. But this was developed for us by them. We also have another sample developed by
Still alive.
Alive, Austria. Um, and yeah, these samples will be both available very soon. Besides the K that we've been.
Yeah, we know from Quantum C# that samples help many developers to get into and understanding the basics of the simulation. Sometimes it's very close to what they want to build, so it's a nice code base to start from. Or sometimes it just can borrow ideas, know how to do some feature that they want to implement in their own game, even though the subject might be completely different. So yeah, we are trying to get from the start these samples up and running for from day one to help understanding the game engine.
And of course I wanted to again mention that especially Martin from Still Alive was a guy who helped us develop the initial version of the SDK. He gave a lot of feedback. He a lot to help us shape uh, various aspects of how the SDK looks like now. So So we used the fact that he started helping us with that, and then his team joined to be first sample the vehicle capture the flag sample, and that helped us also receive feedback from part of the team. And the same happened even more intensely with Dream Loop now. So we got a lot of feedback on things that work, things that were catered to you, and we could the SDK based on that. There's a lot of stuff still to do, but we're as we go. But it was great to have these two different teams already using, and it was kind of a bit of a surprise to me how quickly two teams actually understood all the concepts and did things right, came up with workarounds when they knew there was a limitation that we could fix later with a quicker or a properly designed solution that required something from our side to be. But it was great to see all that. So I hope this is also going to happen when start to use the SDK. They will understand the concepts fast. So it's still a very small sample of the number of developers that use so far, but it was a very good start from my point of view. Very good positive surprise how quickly they understood all the concepts, did everything right. So kudos to the teams. Uh, but I certainly hope that this is going to be the case for other developers.
That's my hope as well.
Yeah. Okay, so I think Daniel that this is a good start uh, for what we have to show. We will certainly do another one to complement on the topics that we didn't talk about today. But I would like to end it soon. And we're still open to questions if someone has a question to ask besides the one that we prepared and already answered. So we'll wait a couple of if anybody has a question, then we'll finish after that.
And we also have the quantum, it's called Quantum Unreal channel in the Circle Discord server. So if you're part of the Circle Discord server, you can ask more questions there as well after the stream if you want. Just share any doubts or any curiosities you might have, and we keep a look on the channel very often. So yeah, you're a guest.
Yeah, same of course. If you ask questions on the public Discord,
Yes.
occasionally I'm there as well, and I may answer some conceptual questions. But of course, this preview SDK is gonna soon be available to Circle members only until it becomes stable. Then when I don't know, we don't have any TAs as always. But once this becomes stable, same goes for Quantum. Quantum becomes stable. That's gonna come sooner than this. As Quantum 3 becomes stable, it will be made available to everyone, not only Circle. Some stuff will still be Circle exclusive. Some samples, I think, custom plugin development exclusive, but the base SDK will be available once it is stable. And the same will be for this one. Start sharing this very, very soon, Circle only, that for some time until it's stable. Eventually, once it becomes a stable version of the SDK, let's call it Quantum 1.0, that, then it will be available to everyone. So since we don't have any questions, stop here and to reach out, Discord, have questions, watch this later. So this is only watched later by a lot of people. So don't refrain, ask the questions, try to answer. So thanks a lot for watching, and Daniel, thanks a bunch for
Yep.
joining me today. And
Thanks for having me. It was my pleasure.
see you everybody next time then.
Take care. Bye bye.